Welcome to Pre-Calculus. This is a unit on sequences and series. In this video, we're going to be tackling sequences. A little bit of a longer lesson here, so we're going to split this up into parts 1 and parts 2. This is sequences part 1. All right, so let's first talk about infinite sequences. One of the most basic patterns in all of mathematics is an ordered progression of numbers called a sequence. A sequence is simply an ordered list of numbers that follow a pattern. So here's a couple of examples. So we have 4, 7, 10, 13, 6, 19, 22. Again, it's an ordered list. So we can call this the first term. The first term is 4. The second term is 7. The third term is 10, and so forth. And then we also notice that it follows a pattern. Hopefully, pause the video if you want to try to figure out the pattern, but hopefully you see the pattern is up 3, up 3, up 3, up 3, up 3, and so forth. So the next term would be 25. Now this next one has a pattern of 3, 15, 75, 375, 1,875, getting big very fast. But once again, we have the first term, the second term, third term, and so forth. So this one might take a little bit of time to recognize the pattern, but if you see it, it's just multiplying by 5. 3 times 5 is 15. 15 times 5 is 75. 75 times 5 is 375. 375 times 5 is 1875. So the next term would be 1875 times 5, which would be 9,375. 9,375. All right, next one is 3, 6, 11, 18, 27. So first term, second term, third term, and so forth. What's the pattern here? Well, it's kind of weird. It goes up 4 and then up 5, then up, up 3, excuse me, then up 5, and then up 7. Oh, so actually it's going up by odd numbers. So it goes up 3, then it goes up 5, then it goes up 7, then it goes up 9. So the next one will go up 11. So the next one should be 38. All right, pretty easy. So we see several different types of patterns there, but that's really all a sequence is. It's just a list of numbers that follow some type of pattern. All right, so generically speaking, again, let's try to be very basic here, right? No examples, just very generic. A sequence has infinite terms. The first term, the second term, the third term, the fourth term, all the way up, and so on and so on and so on. And so mathematically, we could write this as a sub 1, that's the first term, a sub 2, a sub 3. Now, why we use a, I mean, I guess it doesn't really matter. You could really use anything you want, but we typically use a in a lot of math books. So eventually, we keep going up and up and up until we come to what we call the nth term. The nth term would represent any term. NE, nth term, NE. Now, I know NE is spelled with A, but it sounds like NE. So the nth term represents any term we want. And in most problems, what we want to do is we want to write a formula or a rule that describes any term we want. And if we see the pattern long enough and we truly understand the pattern that's going on, sometimes it's fairly easy to write that formula or that rule that represents any term. So again, when you see any term we're talking about, we call that the nth term. It's how can you find any term you want? So now a rule that can find any term you want is considered an explicit formula, okay? Or we say that the sequence is defined explicitly. So if you have a rule, if you have a formula that can help you find any term you want, we call that an explicit formula, and it means that the sequence is defined explicitly. So let's look at 3 examples here. So this first one, or 2 examples, I'm sorry. This first example here says that any term, the nth term, is 3n plus 7. So let's find the first couple terms. So to find the first term, I just plug in 1. I mean, we're not going to continue to do this for every one, but I plug in 1 to find the first term. That's going to be 3 times 1 plus 7. So the first term of the sequence is 10. All right, how do you find the second term of the sequence? Well, you plug in 2. 3 times 2 plus 7. So that's going to be 13. And then how do you find the third term? Well, you plug in 3. 3 times 3 plus 7. So that's 9 plus 7 is 16. And typically, once you kind of get the ball rolling, you start to clearly see a pattern. Next one's going to be 19, then 22, and so forth. Looks like I'm just going up 3, up 3, up 3. Pretty easy pattern there. But again, this is just a generic formula that can find any term we want. So even if I say, what's the 99th term? Well, okay, all I got to do is plug in 99, and I may need my calculator for that. I don't know if I could do that in my head, but 3 times 99 plus 7 is 304. So the 99th term of this sequence is 304. All right, now this next one I chose k instead of n because it doesn't really matter, right? I know it's nice to say any term. Any sounds like an n, any term, but again, it doesn't matter, right? We call it the kth term. It doesn't have to be any term. It could be the kth term. You can use any variable you want, right? It's algebra. So again, if I want to find the first term, all I got to do is plug in 1. 1 squared plus 1. So we get 2. 2 is the first term. And to find the second term, we get 2 squared plus 1. 2 squared is 4. 4 plus 1 is 5. And the third term, so we get 3 squared. 3 squared plus 1 is 3 squared is 9. 9 plus 1 is 11 or 10. Jeez, oh man, sorry about this. And the fourth term, so 4 squared plus 1. 4 squared is 16. 16 plus 1 is 15. So again, we start to see, oh my gosh, I did it again, didn't I? I keep subtracting. I don't know where my head's going here. I'm so sorry. 4 squared is 16. 16 plus 1 is 17. Okay, so we start to see the pattern building here. So it went up 3, up 5, up 7. Logical thinking says the next one's going to go up 9. So 17 plus 9 would be 26 to find that next term. And again, we can check that, right? That's the beauty of having a formula for any term, is to find the fifth term, just plug in 5. 5 squared is 25. 25 plus 1 is 26. But again, this is when these two sequences are defined explicitly, meaning that you can find any term you want. Doesn't matter. All you got to do is plug in the term you want. Now, what is the difference between a finite sequence and an infinite sequence? So an infinite sequence goes on forever, and we typically use the ... right? So here's an example where it's going 4, 6, 8, 10, 12, 14. I'm assuming you can know the next couple. 16, 18, 20, ... means it's going to go on forever. Whereas a finite sequence just comes to a stop. So there is no ... So this is a sequence 3, 5, 7, 9, 11. That's it. 5 terms. We stop right there. It's finite. It doesn't continue on forever. It could continue on forever, but I stopped it right there. So this is a sequence consisting of 5 and only 5 terms. That's finite. Pretty simple there. Now, it is important to understand that there is a second way that we can define a sequence. The first way we just talked about was explicitly. Well, this is a recursive sequence. A recursive sequence is a sequence where each term is defined by its previous term. Now, I know that sounds weird, but the meaning here is that you cannot find any term you want at any time. That's explicit, right? Explicitly defined sequences. If you want to find the 98th term, plug in 98. But with the recursively defined sequence, you need the first term to find the second, meaning I need the 8th to find the 9th. So if I want to find the 98th term, I need the 97th term. But remember, I can't find the 97th until I know the 96th, and I can't find the 96th without the 95th. So recursively defined sequence is you need to know the prior term to move forward to the next term. So these recursively defined formulas look a little bit weird, so let's try to process one together. All right, so first off, before we look at a very specific example, I want to make note of these two symbols because you will see these two symbols in a recursive sequence. So the first is any term. This is going to help you find any term, right? And that literally means any term, so maybe the 9th term. Well, a sub n minus 1 would mean the term prior to the one you want. So if I'm trying to find the 9th term, this right here represents the 8th term because 9 minus 1 is 8. Excuse me. So this is going to be coming up a lot because remember, recursive sequences, you cannot find one term until you know the previous one. And this is a generic way right here of referencing the previous term. So a sub n is the term we want to find, but in order to find that term, we need the previous one, which is a sub n minus 1. So here's an example where that is used. So notice that I'm literally telling you that you can't find the second term without the first term. So in a recursive sequence, I have to give you the first term. Because if I don't give you the first term, then you have no place to start. So here we go. The first term is 3. And then a formula to find any term requires the previous term, which is, again, a sub n minus 1. So what this is a very fancy way of saying, all right, take the previous term, which is defined as a sub n minus 1, times it by 4 and add 2. So the first term is 3. So if I want to find the second term, then I need 4 times a sub 2 minus 1 plus 2. Again, I'm trying to find the second term, so I'm subbing in 2 for n, because that's what you do, right? I'm trying to find the second term. So this right here is the first term, because a sub 2 minus 1, well, 2 minus 1 is 1, so that's the first term. So I'm going to do 4 times the first term is 3, 4 times 3 is 12, 12 plus 2 is 14. So there is my next term. All right, so then if I want to find the third term, I need 4 times a sub 3 minus 1. That's the second term, right? That's the term prior to the third term, plus 2. So again, 4 times the previous term of 14. 4 times 14 is 56, plus 2 is 58. Now, once you get the ball rolling here, you really don't need to continue to show the work. You're just going to say, okay, to find the fourth term, that's right here, to find the fourth term, I need the third term. I need my previous term times 4 plus 2. So 58 times 4 plus 2 is 234. So you realize that these formulas, these sequences get big pretty quickly here. But again, that's the idea, right? Remember, an explicit formula, you don't need the previous term. An explicit formula would be like this, 4n plus 2, where n represents whatever term you want. So if I want to find the 98th term, I plug in 98 and I got it. But that is not what this is. This is not an n. This is a sub n minus 1, which is a, I get it, kind of a weird way of representing the term prior to the one you're looking for. So again, if I'm looking for the fifth term, let's find the fifth term now. I need the fourth term. 5 minus 1 is 4. So I need the fourth term, which is 234. So I'm going to take 234, times it by 4, add 2, I get 938. So that's how recursive sequences work. There are cool ways to define sequences, but again, the drawback is you can't just find any term you want. You have to find them kind of in an order, right? You got to keep moving to get to whatever term you want. So I can't just jump and find the 20th term, because that's just not how they're defined. That's why most students love explicit formulas better, because it's easier if you could just plug in 20 to get the 20th term, but here you cannot. You got to take it term by term to get to where you want to go. All right, so let's keep talking about sequences here. Let's talk about some interesting sequences here, some ones that just are kind of interesting. So this first one is 1 over n. Now that involves n, right? That doesn't involve the previous term, so this is explicit. So if I want to find the first term, I got to do is plug in 1, and I get 1 over 1. To find the second term, I plug in 2, so I get 1 over 2. To find the third term, I plug in 1 over 3. To find the fourth term, I plug in 1 over 4. I mean, how easy is this? Fifth term, 1 over 5. Sixth term, 1 over 6. I mean, I could sit here all day and do this. It's going to get pretty boring, but I could do that. Now, it's kind of interesting to note here that we started out with 1, and then we got a half, then we got a third, we got a fourth, we got a fifth, we got a sixth, we got a seventh. So we are getting smaller and smaller and smaller. So some sequences get bigger, some sequences get smaller. And if you think about it, you know, like the 100th term would be 1 over 100. The 1,000 term would be 1 over 1,000. So if you think about where this sequence is going, it's actually converging on 0. It's getting smaller and smaller and smaller. Remember, what's happening is that the denominator is getting bigger, but the numerator is staying as 1. So when that happens, we're starting to actually converge onto 0, because we're never going to get to 0, because the only way you could get 0 is if you have a 0 in your numerator, which I'm never going to have here. But when my denominator keeps getting bigger and bigger and bigger, the value of my terms are actually getting smaller and smaller and smaller and smaller and smaller and smaller and smaller, closer and closer to 0. So that's a cool sequence to take a look at. All right, this next one isn't difficult, but involves a little bit more time to process. So again, you don't have to show a ton of work here, but you just need to make sure you get it right. So to find the first term, sometimes kids like to plug in a 1. Now, with fractions, it's actually best if you think about numerator and denominator kind of separately. So if I plug in 1, I get a 3 on top. 1 plus 1 is a 2 on the bottom. All right, there's my first term. Second term, 2 on top is a 6. 2 on the bottom is a 3. Now that will reduce to a 2, so sometimes you got to kind of like clean this up. So 3 halves cannot be reduced, but 6/3 can be reduced to a 2. And let me keep going here. So the third term, that was the second term. The third term would be a 9 on top, 4 on the bottom, 9/4. Okay, that cannot be reduced. Fourth term would be a 12 on top, and 4 plus 1 is 5 on the bottom, so we get 12/5. And again, we're just going to continue on this way. Fifth term, 3 times 5, 15. 5 plus 1, excuse me. Sorry, I got the cough. 15 over 6. Now that can be reduced. So again, that can be reduced. They're both divisible by 3. So we get 5 halves and so forth. Okay, so again, just another sequence that involves fractions, and just be careful with that one, please. Once again, my recommendation is kind of treat the numerator and the denominator separately. Find the numerator, find the denominator, numerator, denominator. And then with fractions, again, you have to make sure you reduce if necessary. But again, the cool thing about any sequence that's defined explicitly is if I want to find the 100th term, all I got to do is plug in 100. So that'd be 300 divided by 301. So where's this sequence converging on? Well, notice that this is kind of oh, wait a minute. 101. Oh my God, I'm just full of mistakes today. I'm so sorry. I make mistakes. Let me redo that. The 100th term. Plug in 100 on top, you get 300. Plug in 100 on the bottom, you get 101. So again, where's this going to? And we're talking about where it converges, right? Is it going anywhere? Because some sequences just get bigger and bigger and bigger forever. Other sequences get smaller and start to actually converge on something. So, sometimes you try something even bigger like 1,000. That's going to be 3,000 over 1,001. So again, that number is actually really, really close to what? 3, right? It's getting closer and closer to 3. So if you look at the 100th term, is 300 divided by 101. That's like 2.97. If you look at the 1,000th term, that's 3,000 divided by 1,001, and that is 2.99. So again, this is, like this top one here, this one right here, would converged on 0. We kind of saw that as the sequence continues on, my fractions are getting smaller and smaller and smaller. They're getting closer and closer to 0. For this one, I'm recognizing that I'm actually getting closer and closer to 3. Getting closer and closer to 3. And there's actually a really easy connection here to understand this, right? In a couple moments, we're going to make a connection between sequences and functions. And if you remember, what's happening here is I have a horizontal asymptote. If you look at this as a function, 3n over n plus 1, notice that the degree of the numerator is 1, the degree of the denominator is 1, and when the degrees are tied, you have a horizontal asymptote at your leading coefficients, which would be 3 over 1. So that actually makes sense as to why this is, trying to connect what we've learned in the past. That makes sense that we're actually converging onto 3. So each individual term is its own value, but as we continue to go way off into the infinite future of this sequence, we realize that our values are getting closer and closer and closer and closer to 3. Never going to get there, but they're going to get really, really close to 3. All right, let's look at one more kind of interesting function here. Or notice how I said that function, right? Because sequences are function. We're about to make that connection in a moment. So this one's kind of, I call this a two-parter, right? N is used here to find this value, but then n is also used here. Right? There's no limit to how many n's you can have. So let's see here. This one might make it a little bit slower to figure out. So the first term, if I plug in 1, now, you could probably do this back part by yourself. 2 times 1 is 2, 2 plus 1 is 3. But what this first part does is negative 1 to the 1 is negative, right? Negative 1 raised to the 1 is negative 1, times 3 is negative 3. Now, watch what's going to happen on this next term. All right, the second term is negative 1 squared. And again, the back number you could probably do in your head. 2 times 2 is 4, 4 plus 1 is 5. But now it's going to be positive 5 because negative 1 squared is positive 1 times 5 is 5. And then the third term is negative 1 cubed times 2 times 3 is 6, 6 plus 1 is 7. But again, now it's back to being negative. Negative 1 cubed is negative 1. Negative 1 times 7 is negative 7. Let's just do one more here so you see the kind of connection, and I'll try to explain it. Negative 1 to the 4th times 2 times 4 is 8. 8 plus 1 is 9. And 9 times, well, negative 1 to the 4th is 1. It's negative 1 to the 4th is positive 1. 1 times 9 is 9. So we notice two things going on here. First, we notice the numbers. The numbers are odd. 3, 5, 7, 11, 13, 15. All right, that's pretty quick, easy pattern to see. But we also see this pattern of negative, positive, negative, positive, negative, positive, negative. Now, why is that happening? Well, that's what this is doing right here, right? So this back part is controlling the number, right? 3, 5, 7, 9, 11, 13, 15, so forth. This front part is controlling if it's positive or it's negative. Because when you raise to an odd power, you're going to be negative. Negative 1 to an odd power is going to be negative. Negative 1 to an even power is going to be positive. So anytime we have an even term, we're going to be positive. Odd terms are going to be negative. So I call this a two-parter, right? There's kind of two things that are determining this sequence. And this sequence jumping back and forth between negatives and positive, which is, of course, what that -1 raised to the n does to the sequence. So watch out for sequences to do some weird kind of things like that as well. All right, now I really want to make that connection that I kind of was mentioning earlier. A sequence written in explicit form is a function, right, with a very specific domain of all positive whole numbers starting at 1. So that's the nice thing, right? So the domain is only positive whole numbers because remember, what do you plug in? Well, we plug in 1 to find the first term. We plug in 2 to find the second term. There is no such thing as the 2.5th term or the 3/6 term or the 5/12 term. No, we don't plug fractions in. We plug in 1 for the first term, 2 for the second term, 3, 4, 5, 6, 7. So only positive whole numbers. We don't have such a thing as negative terms. It doesn't even exist. There is no such thing as a 0th term, right? There's the first term. What's the first term of that sequence? So really, these are just functions. So when you write a sequence explicitly, you got yourself a function, right? So here, this is a linear function, right? But listen, -2x plus 4. This is no different. But with a function, you can plug in anything you want, 1.5, 1.7, 2.3, -99. But when it's a sequence defined explicitly, you can only plug in positive whole numbers. So I can only plug in 1. -2 times 1. -2 times 1 plus 4 is 2. So there's my first term. Second term, -2 times 2 plus 4, 0. Third term, -2 times 3 plus 4, -2. And let's go until we see the pattern. Fourth term, -2 times 4 plus 4, -4. Looks like we're starting at 2. We go down 2, down 2, down 2. -6, -8, -10, -12, and so forth. But again, this is a function, right? Each input has an output. I plug in 1, I got 2. I plugged in 2, I got 0. I plugged in 3, I got -2. So each input, what's the term I'm looking for, led me to an output, which is the term value. So again here, this is the first, second, third, fourth, fifth, sixth, seventh, eighth. This right here is the 8th term. How can I confirm that? Well, if I plug in 8, -2 times 8 is -16. -16 plus 4, -12. I plugged in 8, that's the term. I got out the term value. Very, very simple. All right, now there is some really famous sequences out there, and there's actually several, but this is one of the most famous sequences in the world. It's called Fibonacci Sequence. Listen, I can make a video for 2 hours on the amazing features of the Fibonacci Sequence, but I will, save you from that video. But Fibonacci Sequence, honestly, Google it, look it up. It's a sequence that occurs all over the world. It occurs in nature. It's just really awesome. And I could spend hours talking about it, but it is a recursively defined sequence. And it's actually pretty cool because in recursive sequence, we say you need the previous term to find the next term. Well, with Fibonacci sequence, you need the previous 2 terms. So let me just try to make sure I explain this well. So first, the first term is 1 and the second term is 1. But any term you want is defined by taking the term 2 terms ago plus the previous term. So, okay, let's show this, right? If I want to find the third term, plug in 3. 3 minus 2 is 1. So I need the first term plus 3 minus 1 is 2 plus the second term. So to find the third term, I need the first plus the second. Well, I know the first term. I know the second term. That's 1 plus 1. So the third term is 2. Now check this out. To find the fourth term, I need, 4 minus 2 is 2. So I need the second term. Plus 4 minus 1 is 3. So I need the third term. So it's the second and the third term added together. And that's going to be the second term is 1 plus the third term is 2. 1 plus 2 is 3. So once again, you see the pattern, right? And again, it's truly understanding what these represent. This right here represents the previous term. So if I'm looking for the 9th term, that would be the 8th term. And this right here represents the previous term. So if I'm looking for the 9th term, that would be the 7th term, right? So again, what you simply do here is, this is how easy Fibonacci sequence is you just add the 2 previous terms together. So far we got 1, 1, 2, 3. Next term would be 5. So to find the 4th term, we're going to add the 3rd and the 4th. To find the 5th term, we're going to add the 4th and the 3rd. I'm sorry, I said that wrong. Next term is 8, then 11. Not 11. Man, I am just out of it today. It's one of those days you're just not in a great rhythm. Sorry. 5 plus 8 is 13. 8 plus 13. Actually, music. I don't want to mess this up. I feel bad. Is 21. And again, dot, 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 dot. So to find the next term, you have to add the previous 2 terms. It's actually a really, really cool sequence. And again, I could talk all day. Google it. You'll love it. There's tons of great videos out there about it. But again, that's Fibonacci sequence. And this right here is the recursive way of defining it. So again, if I want to find the 10th term, 10 minus 2 is 8. So I need the 8th term. 10 minus 1 is 9 plus the 9th term. I need the 8th term plus the 9th term, and then I'll get the 10th term. But again, if you write it out and you just slowly kind of start to find them, it works out pretty uniquely there. All right, so finding an explicit formula. So once again, now that we've kind of learned about the different sequences, explicit sequences, recursive sequences, what they look like, kind of how to think about them, the key thing here is that explicit formulas are awesome because you can find any term you want, right? So given a few terms of a sequence, we like to then ask you to find an explicit formula to find any term, right? And this can be a little bit tricky, but I want to make sure we're very clear on this, right? Finding a formula to get any term you want is so important because it's very useful because, again, you can find any term you want. But again, finding that formula is a little bit tricky. So what we're going to do moving forward is we're going to break down sequences into 3 types. There's 3 types of sequences in my mind, right? Now, don't quote me on this. This isn't something that all mathematicians look at, but I look at sequences as 3 types. We have arithmetic, geometric, and then everything else. And if we kind of think about sequences in these 3 terms, then we could kind of start to break down the different types of sequences there are and how we could find explicit formulas because they're really awesome to work with. So that's where we're going to end part 1. In part 2, we'll start talking about arithmetic and geometric sequences. But again, this video is more of kind of an introduction to what a sequence is and what they look like, explicit or recursive, and kind of how to get that sequence going. Sequences to me are like snowballs, right? You roll it, and then you keep rolling it, and it keeps getting bigger and bigger and bigger. But you gotta start that snowball. You gotta push it down the hill to get it going. But once you get that snowball going, sequences to kind of find them as they go are pretty easy. All right, see you in the part 2 video for more on sequences.